Hey everyone, today I'm going to talk about Goldilocks. What is Goldilocks? Goldilocks refers to the Goldilocks finite prime field, and all the elements in Goldilocks are integers modular p. And remember, p is a number which is slightly smaller than 2 to the 64, and you can see there are total. The elements are from 0, 1, 2, 3, all the way up to 2 to the 64 minus 2 to the 32, which is the largest element is p minus 1. And Goldilocks is used in Plonky 2 and Plonky 3. And if you are a beginner of finite field, you can think it as a circle. So you can take p equals to 7 as an example. It's a small finite field, 0, 1, 2, 3, 4, 5, 6. We have the rules here, and the code here, you will draw a circle. When you go from, for example, when you go from 6 plus 1, you will is clockwise, you will get 0. So, and 0 plus 1, you get 1. And if you want to minus 1, 0 minus 1 is goes to counterclockwise. You will get 6, 5, yeah. In all the numbers in all the integers in the finite field are a single point on the circle. This may help you understand what finite field is. And for addition and subtraction, they are similar. Like you just compute a plus b modulus p and a minus b modulus p. For multiplying, is also very easy. The tricky one is the division. So multiply and divide, they are inverse to each other. If you want to compute b divided by a, it's the same as you compute b times a to the minus 1, where a to the minus 1 is the multiplicative inverse of a. I will denote it as a inverse. So the next question becomes, how can we compute the inverse of a? Okay, take a equals to 3 as an example. The inverse of a is defined as a times a to the minus 1 equals to 1 under modulus of p. So 3 times its inverse equals to 1. And there is an efficient method to compute it. You don't need to brute force to iterate all the number in the field, so that in order to find the inverse. From Fermat's-Nitto theorem, we know that the inverse of a is a to the power of p minus 2. So p is the prime. P is the size of the finite field. So in division, b divided by a, firstly we compute the inverse of a, which equals to a to the p minus 2. And secondly, we can compute b times a to the power of 2. And here is an example code. You can see we are computing 10 divided by 4. under Goldilocks feed. So here, firstly, we use a fast explanation function in order to compute 4 to the power of p minus 2, and then we get the inverse. And secondly, we compute the result as a times 10 times the inverse modulus p. Okay, this is the very large result, and then we can verify it using multiply. I can multiply the result multiplied 4 equals 10. Yeah, and it's true. So far, you know some basic concepts of finite field and Goldilocks. You know how to add subtraction, division, and multiplication. And let's go deeper. Why we call it Goldilocks? And you must heard of golden radio. Golden radio is defined as this 5 square equals to 5 plus 1. But this is not the form of Goldilocks, because in zero knowledge proof we want FFT, and these primes have very few powers of 2 roots of unity, so that they cannot use FFT and Stark. We instead can see the primes of a modified form, which is 5 square minus 5 plus 1. And if you remember, the Goldilocks prime is in this form, 2 to the 64 minus 2 to the 32 plus 1. And it is happy with FFT and Stark. Why? Because Goldilocks prime must have 5 roots of unity, and Goldilocks has 32 roots of unity, and it allows efficient FFT algorithm and Stark with size up to 2 to the 32. And 2 to the 32 is a very large number, so that Goldilocks is a good choice in zero knowledge proof. And here's one question for you. Why FFT and Stark requires a large root of unity? And you can watch this video for answers. There are also other advantages. For example, efficient modular reduction theorem, and Goldilocks is small enough to fit in the 64-bit number, because it's less than 2 to the 64, and all the modern CPU and operating system, they are in 64-bit. And for free, an efficient inversion algorithm. And if you want to learn more, you can try this blog for more details. That's for the Goldilocks part. Thanks.